Thank you very much. Thank you. Thank you, everyone. And I want to thank a lot the organizers for inviting me here. I cannot describe in words how excited I was when Sakir emailed me. I literally remember myself screaming at the screen. I was like, yes, I'm going. Yeah, it feels so right. That's what I can say. And thank you, Ulrich, for these nice words. I always feel that when people introduce me like that, I feel that I'm a better person than I think I am. Probably I'm doing something good. All right, okay, let's start. Today we will speak about we will discuss, because I would like you to also participate, because no one knows better than anyone. So we will discuss about probabilistic reasoning in deep learning. So first, I will start with an introduction about the basic concepts of Bayesian inference. Then I will actually go into more specific and discuss how Bayesian reasoning can be found or can be applied inside the neural networks and in general inside the deep neural networks. By doing so, I will actually explain the Bayesian paradigm as an approach to account for uncertainty. And as I present, I will explain what I mean by that. And finally, if there is time, hopefully there will be, I will make some connections between the neural networks and the deep neural networks to other so-called non-parametric models, and more specifically, connections to Gaussian processes and to kernels. All right, let's start. Bayesian Inference Basics. When we are called to build a model, what we have is first we have observations. We have, for example, these red dots here are the data that we observe, and they lie on a line. Let's assume that these data are called data y1, y2, up to yn. And the question that we are faced with is to actually to give an answer how this data is generated. What that means is that we are called to actually build a probabilistic model, or a statistical model if you want. That means that we make a distributional assumption about the data. That means that we actually put a distribution over the data y. I'm not sure if the arrow is on well. All right, the arrow is not on. There is an arrow that comes from theta to y. That means that the distribution of y is actually depends on the parameters theta. In this example, here on this plot, I assume that the data come from a Gaussian distribution, and I fit this Gaussian distribution on the plot, as you see. And the parameters theta that describe the model are actually the mean and the standard deviation, the mu and the sigma of the probability distribution. Now I can talk about the likelihood of the model. The likelihood of the model is defined as the probability of the data under the parameters theta. And this is indicated as so. So in order to define the likelihood, I actually take the product of the individual probabilities, because I assume that the data come identically and independently from the same distribution. Okay? That is described by our model. Again, here I remind you that there is an arrow that points from theta to y. But all right, you can sit there. Thank you. All right. Okay. So let's go deeper into the Bayesian world now, and let's talk about how we think in Bayesian terms. What the Bayesian principle says is that all forms of uncertainty should be expressed by means of probabilities, or to be more specific, by means of probability distribution. That means that if in my model I have a parameter that I don't know, then I'm going to put a distribution over it. In my example, I observe the y's, but I don't know anything about the thetas. So what I do, I put a distribution over the thetas, and this is called the prior distribution. What the prior actually does is that it actually quantifies my uncertainty about the parameters, and specifically my initial uncertainty about this. So when I build a model, I don't know anything, for example, in the Gaussian distribution before. Over the theta, I want to put a prior over the mean and the standard deviation. I don't know anything, so I just assume that there will be a prior, and I put a prior over the parameters. Then, however, the next step is what is most important. The next step in the Bayesian inference says how my belief about the parameters is being updated. And this is given by the posterior. Actually, the posterior is described by the celebrated Bayes rule. And what the Bayes rule is actually this fraction here. And it's really interesting to see what this fraction says. This fraction actually says that the posterior distribution is actually proportional to the likelihood times the prior. Intuitively, this means that my initial belief, which is quantified here in the prior, will be updated in the posterior in such a way that I will consider both information from the data, which is the likelihood, and information from my initial belief. So my initial belief will be updated after I see the data. Okay? That's what we say that when we construct the posterior, actually the posterior is constructed after the evidence, after we see the likelihood. In order to give an example, please look at this plot because the colors here are really bad. I'm really sorry about that. And to be honest, I tried many different plots for that reason, but apparently it was not the good choice. So what we see here, I plotted the three distributions. The dark one, the dark gray or dark blue, if you want, is the prior, is my initial belief about the parameters. Then the pink one is the likelihood, is the information that I get from the data, from the observations. And finally, I compute here with the green color the posterior distribution. What I notice from this plot is that the prior is centered more to the left, the likelihood is centered more to the right, and what the posterior says is, okay, you guys disagree a bit, I'm going to take the middle. So it actually compensates for, it actually gets, let's say, it takes the average of the two driving forces. Okay? Put it in very abstractly and very simply. All right? So after we have done that, the Bayesian principle also, or the Bayesian reasoning if you want, gives us a really nice way of actually making predictions. So if now I have, I can use this one. If now I have a point y star, which I haven't seen, what the Bayesian reasoning says is that the way that you're going to predict new values about, if you're going to make inference about you're going to infer new predictions, is actually you will integrate over over the probability of the new point given the parameters, but this is going to be averaged over all the possible values given by the posterior of the parameters. So in very simple words, that means that your new point will take a value, a probability, that it will be given by the generating mechanism here, but this value will be averaged over all the possible values given by the posterior, but the updated value of the parameters. All right? So I take into account I don't consider only one value of the parameter theta, but my posterior actually considers many values. I have a distribution over the parameters, and as such, you can think that I have an infinite number of possible values, and I average over the possible values of the unseen data, given this infinite number of possible values given by the posterior. All right? So, question now, why is this useful? Why do we even care? First of all, it should be clear by now, hopefully, that in this way, the Bayesian reasoning is it feels right, it's intuitively right. When we have unknown parameters in a model, it's better if we are flexible about our beliefs of them. And that, in probabilistic terms, means that we need to put a distribution over it. In that way, I quantify my uncertainty about the parameters, as opposed to having point estimates to consider that there is only one value for these parameters. Okay? We cannot be strict. It's better not. We can, but it's better not. That's what the Bayesian framework dictates. Also, by taking the Bayesian route, we can actually impute missing data. What we mean by that is that any parameter that is unknown can be sampled from the distribution that we first define with a prior distribution, and then we update with a posterior distribution. So our model in this way is what we call fully probabilistic. So I have the y's here that are sampled from a distribution given the theta, and then my thetas that might be missing, that I don't know, I can sample from the updated posterior distribution that is actually given by the Bayes rule that we described. All right?
Say that again, sorry?
Yeah.
Say the last point again.
So when I say, yes, I can repeat. I think it was a long sentence, my bad. So using the Bayesian framework, we can impute missing values. By missing values, you can think that you have a parameter and you don't know anything about it. But since you put a distribution over it, you can sample from the distribution, and you can actually get examples, or you can get values of the parameter, points of that parameter.
The parameter or the data?
The parameter. The data follow a generating mechanism, which was long time ago, which was this one. It is also a distribution, but when I say that I can impute missing values, is that I can sample from the posterior over the unknown or the latent parameters. Okay? This is just, let's say, an accepted notation in the literature. Right? So the final point why the Bayesian framework is useful is has to do with our meeting here, is that it naturally addresses issues like regularization and overfitting, and this is very, very, very important for models like the neural networks and deep neural networks in general, as we will see and I will discuss in more details later. Now, so let's go now and talk about Bayesian, about the stuff that we just discussed, about how this stuff can be applied in the neural networks and the deep neural networks. First, I will start with an overview of the neural networks, and I'm sure that you have heard about what a neural network is by now very often, a lot, but a reminder is always good.
Just to take it back, to get the posterior distribution, it depends on the curve. But apart from literature, where you try to find out what the curve distribution is from literature, is there a clever way of trying to guess the curve distribution so that we can get a posterior distribution? Because certainly when we get the distribution wrong, it affects the posterior distribution. So apart from literature, is there a clever way of guessing the curve distribution?
Well, there is I think there are two answers to this question. The first answer is that clever is a very subjective term. Maybe when you see a lot of data, you get a sense of how they are generated. So you can get more like a good. Sorry, in a while I'll get to you. you can get more like a better, you will get a better idea of what the prior should be. So the more data you see, the more information you have, the better the model will be. So you can build a model better, and by that I mean you can put a better prior over it. The other answer is that people in general, because in most of the cases you don't have enough data, what you do is that you put what we say simple priors, and by simple I mean other conjugate priors, the ones that will give you a good posterior, in the sense a posterior that you can sample from. That means that the product of the likelihood and the prior that you chose will give you a posterior that you can sample from. So you choose your prior in a clever way so that your model is easy to apply inference on. And the other method that people do is that they put what they say vague prior. That means a prior that is non-informative. It puts like it puts the same mass in every value. Because in that sense, you care about the evidence that comes from the data and not from the prior. So I don't know if this answer covered you or... So there is no clever way. In my opinion, it depends on what you want to do with your model and what the data feels like. And also, by experience, you become better and better. Or you just go for Gaussian always. Yes, yes. In my example, I was using a Gaussian distribution. This is the generative distribution. I didn't specify the distribution over the priors. So this distribution here is the distribution that I sample data from. It's not the distribution over the parameters.
When you do your integration, you integrate over theta, and in that example, your theta is the specification for your normal distribution. And can you also use something like, say, a theta distribution?
On the theta?
No, for your, carry on.
Here, for the y. For the posterior.
One more. For that integral. You're integrating over theta, right?
Yes, I integrate over theta. Here I compute the unseen, the probability of the unseen point. I know this, I don't know this. I need to integrate over this. Okay. Okay, we're good? So yeah, let's start. So first, as I said, I will make a brief introduction, like a brief reminder of what the neural networks look like, and then I will talk more specifically how we can apply the Bayesian framework on them in different cases. So this is the plot that probably you have seen a lot by now. So we have here, what I have here is a deep neural network. I have the input layer, the output layer, and have like probably a really big number of hidden layers. And what it does, I have the input that goes inside this many layers, and I get the output. What happens here, we will explain briefly, and probably you can tell me as well. You should know now. So in general, what the deep learning is actually a fancy framework of building flexible models. And by flexible, it's just building like fancy functions over inputs to get some output. Okay? And the function is actually the result of all the functions that are happening here, of all the magic that is happening inside the layer. The probably very big number of layers. If we look closer now, we will realize, please look at this plot, we will realize that there is some building blocks, or some units, if you like, that are being repeated. And for example, we have here in the first layer, in the second layer, we have 5 units that take the input from the the input layer, that take the signal from the input layer, and then in the second hidden layer, we have 5 units again, and each of them take the input as input the output of the previous layer, and so on and so forth. This is the beauty of the deep learning, of the deep neural networks, that actually you can repeat these building blocks in many ways, serially and in parallel, and actually you can do a lot of fancy stuff with that. But let's look, or let's remind ourselves how these building blocks look like. In the very simplest case, which is the unit in the first layer, what we have is actually a unit that takes as an input a multivariate variable x that has m dimensions, x1 up to xm, for example, and then it combines them in a linear way using some weights vita, and we have m weights as many as the inputs, and then this linearly combination of the inputs are plugged into a nonlinear function f, and it gives us the output of the unit, or the network, if you like. So to put it in a more compact way, what it does is we have the input, then it enters a box, and in the box we have the linear component that combines linearly the input, and then we have the nonlinear components that takes as input the linear component and applies some nonlinearity on it and gives the output of the unit. Okay? These are terms that have been used extensively. This is actually a regression, and there has been, let's say, a regression has been extensively used in statistics with different terms, where the weights, while now the vitas are called weights, they are also known as coefficients. And the inverse-link function f is now known in the neural networks area as activation function. Okay? So we'll be talking about linear components, about nonlinear functions, about activation functions, and about weights of the network. All clear, all known by now? Okay. So we take this unit, as I said, and in each layer we repeat that in each layer, and until we reach the output. So in each layer, the input is linearly composed, and you need also to notice here that depending on which layer you are, the input differs. So for example, if I am in the middle layer here, the input that this layer will get is actually the output of the previous layer, and that output might be an output from a nonlinear function, as I described. And then, when it gets this linear combination of the input, it applies a nonlinear function. And the deep neural network is constructed by a recursion of the process I just described. And this is a slide that gives this, this story in a more compact way. We have the input, we have the output, and in the middle here we have the deep neural network structure, which is actually a repetition of the blocks we described. And in another way, it is actually a composition of many nonlinear functions. And by actually doing this approach, this methodology, what we actually achieve is we are able to represent functions of interesting complexity. Okay? Let's view now the unit, the block, this block that we are seeing as in a probabilistic view, having a probabilistic view, as a probabilistic model. I plot here again the building block. Here again I have the linear component. And a way to view it probabilistically, as I said, is by making some distributional assumptions about the output. But wait, what we described so far is that, okay, we have a linear combination of the input. You put this linear combination into a nonlinear function, and you get the output. This would be like non-stochastic. Why are you putting a distribution there? Well, you can put a distribution based on what you want to do. All right? We can, for example, you can just, in the output of this network here, you can put some noise, some Gaussian noise. Example, to make it more clear, an example of regression. In the regression, the output of the network here is the activation function here, f is identity. That means that it gives as an output just the linear component, the linear combination of the input. By doing so, the output now is given, the output y, sorry, the value y, the observation, is given by the output of the network plus some noise, I said. And the noise comes from a Gaussian distribution. So by adding noise, I added stochasticity, all right? I added some randomness. So now I can safely assume, I can safely state that my observations come from a distribution, which is a Gaussian distribution, that has as mean the output of the network, okay? That's how my unit now does regression. Question now, how do we train the network? And by training the network, we actually need to learn the parameters of the network. We have already discussed in this school, in this meeting, a lot about the training. Mark also mentioned that a lot. So one way to actually learn the most used way is by the principle of the maximum likelihood. And what this principle says is actually that I take the log, the negative log likelihood of the probabilistic model described by the network, and then I'm trying to minimize it. Or in other words, I'm trying to find the value of the beta, which is the weights of the network, that minimize this function, this negative log likelihood. Let's do that probably in the example of the regression. I plot here the regression as, I describe here the regression using a graphical model, the regression given by the network. So since this is a regression by a neural network, I have in one node, I have the input, and in the other node, I have the observations, I have the output that I am interested in. It's probabilistic. I see it as a probabilistic model. That means I need to apply a probability in the output. I need to make some distributional assumptions about the output. So as I described, I consider that the observations come from a Gaussian distribution that has as mean the output of the network. And if we compute the negative log likelihood of this model, then we can derive the cost function, which is now called squared loss function. And it has this form. All right? We now compute the point estimate of the maximum likelihood of the weights by methods that are being used in the neural networks, and that is using stochastic gradient or backpropagation and so on and so forth. All right? However, now, what we did is we computed a point estimate. So just a value of the parameters that actually minimizes the negative log likelihood. That's the principle of the maximum likelihood estimation. This has nothing to do with Bayesian, though, so what am I speaking now if I'm just repeating the maximum likelihood and I'm supposed to be Bayesian? So let's be Bayesian. So in the Bayesian framework says that we need to put the prior over the weights so that our beliefs, after we see the data, are being updated in the posterior. Again, the prior, the evidence, which are the likelihood actually here, and my updated beliefs quantified in the posterior. All right? The pros about this technique of the Bayesian framework now in the neural network is, again, we quantify the uncertainty. We don't only estimate one point, but we estimate a distribution over the parameters. And by doing so, we will see that we actually are actually adding some regularization to our const function, which is really, really good in the neural networks, to avoid overfitting that we actually observe a lot in the point estimate method. Clear? Good. All right, let's see how we do that. Now, I consider the beta, which are the weights of the network, I repeat. I consider them as unknown. And since I'm Bayesian, I'm going to put a distribution over them. All right? And in my graphical model, I add a node that points now to the observations, to the output, if you like. My model now has changed a bit. I consider the prior over the weights. And given the prior, given the parameter beta and the x, I now generate data from a distribution that depends on x and the parameters beta. Okay? So I have the prior and I have the data generating mechanism. My additional step is that I put a prior now over the parameters, over the weights of the network. The Bayes rule says that I'm going to compute the posterior as the product of the likelihood and the prior. And the maximum a posteriori principle now says that after you compute the posterior, you're going to compute an estimate of the parameters that actually minimize the negative log posterior. What's the difference now? I don't minimize the negative log likelihood. I maximize the negative log posterior. Can someone tell me what's the difference? What we expect to see differently here by minimizing the posterior and not the likelihood? Exactly. By doing that, we are taking into account some information from the prior. Let's see an example. Going back to example of our regression, now we have put here, since the weights are the weights of the network and it's like we consider them as a multivariate variable, I put a multivariate Gaussian distribution over them with some parameters here, lambda. Okay? And I described here the data generating mechanism again. So this is my prior. By using this probabilistic model, my loss function now, which is the negative log posterior, takes this form. If you remember, the first one, the first term, is actually the same term as found in the maximum likelihood estimate. What is different now is that we have one additional term, which is this term. And this is exactly the beauty that arises from using a posterior distribution, from computing the posterior distribution. What this term is actually a natural penalty or a natural regularization. And if you play a bit in your mind that, or by experience, you realize that what it says is that this penalty actually penalizes, this term penalizes values of the weight that are too big. So by using this penalty, by using the Bayesian framework, the inferred weights cannot be very big. So our network cannot oscillate. Yes?
Different priors actually have two different regularizations. So can you tweak the regularization by choosing the
Of course.
So
Yes. Lambda here comes from the prior. So the lambda is also really essential.
So what can you give us some examples? So can you do one regularization with quantifier or like, is this something simple you can say about?
Sorry?
Yeah, what is one regularization corresponding to the prior?
I think, if I'm not mistaken, I think this is the L2 regularization. Yeah.
What does L1 correspond to? L2 is normal.
I'm not sure about that. Sorry. Is the Laplace? Right. There's a Laplace. You're right. Yes. Yes. It's not squared. You don't take the product of the vectors there. Yeah. Thank you. All right. Okay. Did this answer the question? Yeah? Yeah? Okay. So,
How complex is the derivation
how complex is the derivation? If you take the gradient, you mean? If you take the gradient. How you take? Okay. You compute the negative log. Sorry, I thought in my mind like the chain rule and stuff. If you take the negative log posterior, and the posterior is the product of the likelihood times the prior, so you compute the log of the likelihood and the log of the prior, and since I play with Gaussian stuff here, it's really easy to derive.
How do you choose m beta, the mean of the norm for the prior?
You can actually put a prior over it as well and learn it. Otherwise, you can go for 0 in the beginning, small values. Usually, it's good to start with small values in the networks. Question or no? Okay, now I still computed, although I put the distribution over the parameters, the posterior, and I computed the posterior distribution, I still computed a point estimate, all right? I mean, I still got the beauty of the regularization term here, but nonetheless, I had like a point estimate still. The way I do predictions now with using this point estimate is I plugged it into the data generating formula here, distribution here. You see here that the mean now depends on the point estimate, and that's how I make predictions as a sample from the generative model. All right? So it's not fully probabilistic yet, right? I put, but let's see what we have and what we have not. I have been Bayesian over the weights. I have put priors over the beta. And by that, I ended up having a better loss function in terms of I have regularization terms, okay? That help me avoid overfitting. What the neural networks or the deep neural networks don't handle in my talk so far is missing data. And if you remember, I described what missing data is, missing values. In my neural network, I have the input and the output. I talked about the data generating mechanism of like putting a distribution over the output that depends on the input and the parameters vita. I talked about putting a prior over the vita, the weights, but I didn't say anything about the prior over the input. Okay? And not having a prior over the input, that means that I cannot sample to get, I don't have a distribution to sample in order to get values for the input. So there arises the problem of the missing values. I just described that. Also, the neural networks don't generate new examples. And as an example, I actually mean both the pair of the x and y's. If I want to generate both pairs of x and y's, I cannot. I don't have distribution. That's because I don't have a distribution over x. Okay? And as in extension, I don't have a joint distribution over x and y. That is needed in order to generate new examples. Okay? So there is a need for a fully probabilistic model that actually does that. And what is that? Puts a prior on every parameter of the model. And that's what I'm going to describe right now. And an example of a neural network that actually is fully probabilistic and actually is used in unsupervised learning, surprisingly, is what we call autoencoder. And it's really interesting to see. An autoencoder, in its simplest form, looks like this. What is this? Is actually a neural network that has 3 hidden layers, input and output. What the autoencoder does is that it takes an input, y, I call my input y now, and there's a reason for that, takes that input, applies some nonlinearity, as we described, and gives an output in the intermediate layer, which the output now, this output is called code, or latent representation of the input. So in simpler words, what it does is that it takes an input, and it changes the representation of an input into Z, which is the code representation of the input. Okay? Then, the second part of the autoencoder takes the code, the hidden representation, and it actually tries to recover the initial signal, the initial input. Funny. So, it has 2 parts, the encoder and the decoder. The encoder takes the input, changes the representation, and the encoder takes the changed representation of the input and is trying to recover the initial signal, the initial input. And the target of the autoencoder is actually to reconstruct the output, the initial input, to reconstruct the signal in the output by minimizing the error, the reconstruction error, which is given here by the square laws. Okay? I find, and I think this model is very interesting because it's all about unsupervised learning. And by unsupervised, I mean that the autoencoder, the way it sees the data Y, that the way it experiences the data Y, is that it sees the data, it takes the data as an input, the observations Y as an input, and it's trying, or it does put a density, probability density function over the data. It computes it, it finds it. And when I say I find the distribution, it means that I find the parameter over the distribution that define the distribution. And in my autoencoder here, the distribution here is the conditional distribution of Y given Z, which is applied here. And Z is latent. And since it's latent, I'm going to put a prior on it. Let's see how this is done. Is this clear, guys? This is unsupervised? There is no pair of input and output. It's not that I have an instant of input and an instant of output that I know. I only have Y's. I put them in the input, and I observe the output. Okay? Yeah?
So with the structure of this model, is the idea to kind of compress the input to forces structure onto the, kind of simplify the structure.
Exactly. That will be my next point, yes. That's why it's used. The main use of the autoencoder is for dimensionality reduction. It actually offers a different representation of the input. And by different, in most of the cases, is that by applying smaller hidden units than the dimensions of the input inside, it provides a smaller representation of the input. All right, let's see now what's happening inside there and why I like autoencoder as a fully probabilistic model so much. So again, here I have the plot, the graph of the autoencoder, and down here I have the graphical model of the corresponding graphical model. I have in my input here, I have the observations. I plug them into the model. Then I have in the middle layer, I have the latent representation Z, or the code of the autoencoder. And then I have the output, the signal generated by the model. In between, what happens is magic. It's beautiful. So since it's fully probabilistic and it actually involves 2 neural networks, this one, the encoder and the decoder, I said that both of them are constructed probabilistically. That means, I repeat myself so much, but I think it's the best way to remember stuff. That means that I assume that the output of its network, of its part of the autoencoder, has a probability distribution. So in the first part, I have the autoencoder, and the output is the hidden code. So since this is a probabilistic representation, I'm going to apply a probability over Z, and this is given by this conditional probability. Probability of Z given the data, the Y, the input, okay? The same here, I have the decoder. The decoder is also a network, and I'm going to use it probabilistically, so I'm going to apply a distribution over the output. So the distribution over the output Y will be a distribution that depends on parameters theta, and it's a conditional on Z. Note here that both distributions depend on parameters, phi and theta. Phi is the weights in the first part of the network, is of the weights of the encoder, and the theta are the weights of the decoder. Okay? Yes?
I think I'm getting lost now. So in the previous model, you said we can't sample from it, right?
Yes. We can sample we can sample the input. What I said is that this is the model, the previous model. I don't have a distribution over the input, over the X. I don't know anything about the X. But not here, this is supervised. That means I observe both X and Y.
Okay, cool. So what are we trying to address by moving on to the autoencoder?
What I'm trying to address that by moving back to the autoencoder, that now I can apply a distribution over the parameter that the generating mechanism depends on. I'm going to explain that. So what the decoder here does is, this is the distribution that generates the data. If I sample from this, I sample data. I sample observations, okay? So now I say that I don't have missing values because now, using the autoencoder, I can also sample from the input Z. And I'm going to make this clear why this is happening. In the decoder, I have the generative model, which is the hidden that gives the observations. So I have a data generating mechanism that depends on the Z, the hidden code, and I also put a distribution over the hidden code. Okay? So now I can sample from this. I can sample first from Z, and given the sample value, I plugged it into this conditional, and I can sample a point.
Is it possible for your, so when you're taking your Y, I think you know what those Bayesian variables, is it possible to have like a analysis so that you can like come back, so once you go into Z, you can't go back to Y? Does that happen?
So you mean because I use the Y twice?
Sorry?
Because I use the Y twice?
So let's say that you had two different Ys. So when you encode them into Z, you get the same value. Is it possible to have like that?
No, it's not. It's not deterministic. You will never. You will update your posterior, the distribution over Z. Maybe I don't get your question.
So what I'm trying to ask is, if you had maybe like two vectors, 1 and 0 and 0 and 1, this is probably a bad example.
The input and the output of the autoencoder.
Sorry?
The input and the output of the autoencoder. You mean? Oh no.
The input to the encoder.
To the encoder.
Is it possible for two samples that don't look the same to get mapped to the same latent states or at the same?
Oh yeah, that depends on how you. That depends on how you construct your autoencoder. Yeah.
How do you know? So when you're constructing this stuff, like how do you know I'm supposed to, bring it like this so that I don't have any problems? Or is something that I see because I can't recover the Y data, so that I'll be around that.
Well, that depends on your cost function. Here, in my simplest case, that will define two different points. maybe Mark can.
Maybe a quick comment. Can you think of an autoencoder as a lossy compression of the data? So you lose something by doing this.
Yeah, that's a good answer. Yeah.
So it can happen that you have two different inputs, you map them to the same code, and you can't reconstruct them. It's possible.
So if there's not supposed to happen, how do I fix it?
So you try to model in order to reduce this data.
Yes.
Do we learn a file out of Z, or do we choose a file out of Z?
We choose a prior always. I mean, there's ways to learn the prior, but you go crazy in hierarchy. But here, you choose. It's a Gaussian here. Yeah, well, it's like, it depends on it will take the mean will be the output of the network, and then you add some noise. And you have some trick there, but it's not important. Yes.
Does this happen, like, I'm totally lost. Does this happen before training or after training? Like, is there training involved?
I didn't get to that point yet. so it's really crucial to understand that the autoencoder consists of two different parts. The generative part, which is the decoder part, is the one that actually you can generate data from. Okay? So think of it like, actually now I only have this model. This is a latent variable model, which means that I have this latent variable here, Z, and then I have the data generating mechanism here that generates the observations Y. Okay? And this probability over the Y depends on the latent variable Z. Okay? And I put a prior over the Z, and that's how I generate data completely. Okay? Well, maybe I'd say in the notation a bit. Well, theta, why is it confusing? Theta is the weights of the network. It's still the weights. I will explain how I learned the theta. So I think, yes. Well, I think what you are saying, maybe I'm wrong, correct me if I understood wrong, is now that I have actually three variables that I'm playing with, the Z, the Y, and the theta. The distribution over the Y depends both on Z and theta. So the theta is the weights of the network and are still being learned using the backpropagation and all the stuff we know, while the Z now here, it has to be learned in a different way. It's because because it has a distribution. Okay? Yes?
Do you inject noise the same way we did in the previous model? Like how you added noise to the output?
No, you don't in the output, no, because you want to the model. Sorry, in the generative, here in the generation, yes, you can add. In the generative, yes.
The same way we did before. The output, we added noise. Otherwise, it's deterministic. You made a point about it.
Okay? Yes. I just, okay, I'm good in time, yeah.
I just want to one thing clear. So Y is a vector of values, and missing data means you don't know some of the elements in that vector.
In the Y, you mean?
Yeah.
In this case, missing data can be any data that come from parameters. That as a realization of a parameter, as a value of a parameter.
So the whole Y is missing.
The Y, you observe the Y, and you put it as an input to the autoencoder, and then you get as an output. You get an output. The Y is not missing. but the y, but you can actually think like that. The y is explained in a way by z, and that is missing. It has a hidden representation z, and we don't know it, and we're trying to find it. That is missing. Yes.
If you have a missing value in your input to your encoder, and you replace that value from your Z state to your decoder, you take that output from your decoder and feed it again into your encoder, and does that iterate?
Yeah, you can do that. You can impute that like that. But if you have a lot of missing values and you do that, you actually generate only from the model and you overfit. Okay, I need to go on now. I'm happy to take questions later. I hope it's slightly clearer now. So let's go back again to the slides. As I said, we have the two parts. The decoder part is actually the generative model, is the one that actually describes how I'm going to sample from the model. And what it says is, I define a distribution over the y, and this distribution depends on a latent variable z, which is the latent representation of the signal. Okay, and I'm trying to learn it. I don't know it, so I put a prior over it. So the question is now, okay, how are you going to learn the z? Sorry, I call it zeta because I'm Greek. How are you gonna learn z since this is latent? So, okay, I'm Bayesian. I'm going to learn the Bayesian way, and the Bayesian way is by actually computing the posterior. And this is actually defined in the first part. The inference, the whole Bayesian inference, is actually defined in the first part of the autoencoder, which is the. Sorry, I think I'm missing that. Which is the encoder. What the encoder says is it takes as an input the observations here, and it points to the latent variable z. And since this is probabilistic, now I'm going to apply, it defines a probability distribution over the latent variable z, given the y, and z given the y is the posterior. Okay? And this distribution, the distribution of the posterior, now depends on phi, which is the parameters, the weights of the encoder network, neural network. Okay, two parts, the generative and the inference. In the inference, I learn the posterior, the Bayesian posterior. In the generative, I sample from the model and I create new data. The generative part has nothing to do with observations. It doesn't see the observations. It creates new ones. The encoder sees the observations and it computes the posterior. Okay? So, in the inference now, I need to learn both the distributions, P of f, P of theta, and also, which actually means I need to learn the weights phi and theta. All right. If we now look at the posterior, I'm going to be I'm trying to present it in a simple way because it can get really confusing, more confusing. So what the Bayesian posterior says of the latent variables in the inference part of the encoder, if I take the Bayes rule, if you remember this is the Bayes rule, well, the problem with this probability is that I cannot compute it, I cannot sample from it. That means, as Mark very nice said, clever said, I cannot, we don't have a name for it most of the time. So I cannot sample from it. Okay, but why is this a problem for me? This is a problem for me because if I cannot sample, I cannot construct it using the weights in the network. What I do in the network is I construct distributions using the weights and the connections of the network and add some noise. If I don't know if the distribution that I want to construct doesn't have a good form, I cannot compute the weights. I cannot do anything. So I want a distribution that has a good form. So what I do, I follow the variational Bayesian inference and says that, okay, approximate the posterior that you don't like and doesn't suit you with the one that does. And usually the one that does is a Gaussian distribution. So, yeah. Sorry guys, this is the truth. So that's how I use an approximate distribution to Q, which I call Q now, to approximate the posterior, the ugly posterior, or the posterior that doesn't work for me. All right, this is a step. It's a nice step that also implied by Bayesian. But again, why is this Bayesian? Okay, it's Bayesian because the posterior that I take here and I try to approximate with the distribution comes from the Bayesian posterior Bayesian rule. Okay, I'm still Bayesian. I haven't deviated. Okay. All right, what it does in a very simple plot here. If this true posterior looks like that, it has some modes. What I do is that, okay, approximate this true posterior with a simple Gaussian. And instead of the true posterior, now start using the approximation one. Okay? Again, you plug that into the encoder, and how do you construct this distribution in the encoder? You choose the weights and add some noise. Okay? How I learn the distribution? I learn the weights of the network. Okay, I did that. How free am I to choose the distribution? Okay, you cannot choose whatever distribution you like. There should be a metric that will actually say how good your distribution is. And by good, it means how close to the true posterior the distribution that you chose is. And this is the Kullback-Leibler divergence, KL here, that actually measures the information lost when using Q instead of P, in a very abstract way. Okay? And you will see that this is very good because this actually will appear in my cost function for the encoder. So, question now, the cost function should have what? Should have a measure that says how well my autoencoder does. And what this means, since my autoencoder is trying to reconstruct stuff, it should have a measure that says how well the data generating mechanism in the output and the latent distribution phi do. P over Z, sorry, that do. Okay. Again, I'm minimizing the negative log likelihood. And if we actually do some maths here, after the computation of the negative log likelihood, we see that the cost function now has two terms. The first term is the expected log likelihood that measures how well samples from the approximate distribution explain the data that you see. And now, the beauty of Bayesian inference here is the penalty, which is the KL divergence that arises here. So you don't only care about the reconstruction, but you also care about how well you choose your Q, your approximate distribution. So I didn't come up with that. This came up after doing some maths in the negative log likelihood. And I see that I have this pretty cost function that is very intuitively right. All right? Okay, penalties derived from my model, and I didn't have to plug it in ad hoc. All right, what did I manage to do now? I managed to have a principal inference approach inside the really capable framework of deep learning, of deep neural networks. And the penalty or the regularization, if you want, is intrinsic part of the model. I encode uncertainty and also can impute missing data. So what I will discuss now in this part of the talk is how we can see the deep neural networks and not just the neural networks in a different way, and more specifically as a kernel method. You don't really need to know anything about kernels. What you need to know is actually that in the kernels methods, every kernel method, what does, and actually makes it important and different from the rest, is that for the predictions, it actually uses all the observations explicitly, all the data that we see. And I will try to make it clearer as I go. So far, the neural networks, using the point estimates that we discussed, they make predictions using these point estimates, and these point estimates are being computed by minimizing the log likelihood. And as such, all the information I have about the data, from the data, is being distilled into the parameters, the weights, for example, here, using the maximum likelihood estimation, okay? Once I compute the point estimate, I forget about the data I have seen. All the information from the data is inside the maximum likelihood estimates or the maximum a posteriori estimates, okay? Now, what about storing the entire training set? And by training set, I mean the entire observations I have, in order to make the predictions. Let's see, can we do that in the neural network? The answer is that we actually can by using some fancy maths, which I won't present very much here. I will just briefly, as an overview, present. All right, again, this is the structure of a deep neural network, and the example I'll be using again is the simple example of regression. But now I will be using the regression looking at the unit, for example, at the last layer. And what I have here at the last layer, I have as input the nonlinear output, the output of the nonlinear function that comes from the previous layer. And now I represent the output as phi, is a function because it's a nonlinear function, is the activation function that comes from a layer. And I take a combination of these nonlinear functions. Some people might know this function as a linear basis function regression, basis functions, okay? So here a reminder to have this as a picture in the mind. I try to minimize the cost function that I'm using again is the one depicted here, is the cost function actually that has the sum of the errors, and the penalty term is the one that we discussed that comes from the maximum a posteriori. So I minimize that by taking the gradient, and I compute the maximum likelihood estimate. Actually, sorry, I will correct myself. Here is not the regularization term. Here is plugged in. It doesn't come from the posterior, but it looks like, because I made it look like, but I still use the maximum likelihood estimate of that cost function. Again, as I said, the predictions now are computed by plugging in the maximum likelihood estimate to the regression function. So I take the estimates of the maximum likelihood for the weights, and the output is a linear combination using this of the basis functions, using these point estimates. So what is the takeaway message from this slide is that the predictions are fully based on the length parameters. We don't use the training data, we don't use the observations, and all the information from the data is just introduced, transferred through the point estimates. So that's why this approach is called parametric. In order to make predictions, I use the data implicitly through parameters, through point estimates, okay? Questions? Okay, let's change now that, and let's try to be non-parametric. What we do, I'm just doing some maths here. I take the gradient, I compute the maximum likelihood estimate, blah, blah, blah. I rearrange some stuff here, and I write the maximum likelihood estimate as a linear combination of the basis functions. But now the weights are alpha, and alpha is given by this. Why am I doing that? Because I need to, for the next step. In the next step, I take again the gradient, but now of the reparameterized cost function in terms of alpha. If I do that, I compute an estimate for alpha, and that estimate now, it looks like that. And what is important here is, first of all, this matrix and this data, the y. So this estimate has a function. This matrix is actually, each element of it is a function that takes as an input the original data points in the original data space, and depends on the data y. The data y are the training data, are the observations. Okay, this is confusing now. I put so many things, so many equations in one slide. Right. What I did is, from the point estimates of the maximum likelihood, I rewrite them using some mathematical magic. And I find a point estimate alpha that depends on the data. Here, I didn't have the training data. Here I do. No, that was not right. So now the interesting part is about the predictions, how I predict an unseen value y. In the first case, in the maximum likelihood estimation, I just plugged in the estimate in the regression equation, okay? No, and that estimate here is different from that one using the reparameterization given by alpha. The reparameterization given by alpha computes the unseen data using this formula. This is just simple math derivations, sorry. Oh, wow. Sorry, guys. Thank you, bye. Okay, again, we need to have this done. All right. The first estimate of the maximum likelihood, the reparameterization given alpha, the predictions now, the maximum likelihood estimate is given by here, while the prediction by alpha is given by that. What's the difference here? In the point estimate, I don't use any kind of training data. I don't have memory of the training data. While here, now, using this reparameterization given alpha, I'm actually able to explicitly use the training data to compute the predictions, to answer about the unseen data. Yes? Okay, the advantage of doing that is that's a good question. Sometimes it's way easier to define this function here that actually acts in the original input space than defining the basis function f here. It's way easier. So, of course, now stop using neural networks. I'm just using kernel methods. Okay? But my point here is that from neural networks, from seeing them as parametric, I can go to non-parametric, and I can actually show that the deep networks are actually duals of kernel methods. And I have to say that this part of the talk is a very good part copied from Shakir's slides in his website. Has a beautiful, Shakir, I'm talking about you, has a beautiful explanation about the stuff. So yeah. All right. So in the last part, which is actually only 2 or 3 slides, I will become Bayesian again and step back and say, okay, I have this model again. I have this model again of my linear regression unit. And what's the task? So far, what I'm trying to do always in all these slides, I'm trying to learn I'm trying to learn the weights of the network. And by learning the weights, what I'm actually learning the activation function f, here, the function here. All right? Okay, if you're going to learn the f, what about if you think the f of f as random, which is actually random? By thinking of f as random, maybe I can put a prior over it. But wait, the f is a function. Well, yes. What we can do is that we can consider a vector bold f that actually puts together all the points that I observe, all my observations, that come as an output from the network. Okay? I put them in a vector, and I put a prior over the vector. So in that, I'm really sorry, but I think it's like, so in this scenario, f now is a multivariate variable that has that the dimension of f now is as big as as many data points I have. Okay? I apply a distribution, And usually the distribution that I apply is, in this scenario, is a normal distribution, a Gaussian distribution, okay? It's getting weird. I can see you here. Another space. It's like, maybe it's like deep Gaussian, yeah. But think of it like, I have all the points, all my observations in a vector, and I put a prior over them. It's just like a multivariate variable, and I put a prior over this variable, and in my case, the prior is a Gaussian, a multivariate Gaussian, okay? Think of it like that. It turns out now that I want to have a connection between what I did now and with a neural network. Well, the connection is that it turns out that if I have an infinite number of units, and I put also like a Gaussian prior over the weights, and when I have an infinite number of samples, then the prior over the F is actually a Gaussian process. Funny? Well, and then it's like, then it's just math, and you can actually compute all the missing values of the unseen data by integration, by Bayesian integration, where you know all the values, and you're done.